to wrap up this section, I've got one more theorem and then a few notes that are related. It says if series sums to A and a second series sums to B, they're both convergent, then you can add them together, subtract them, or multiply by a constant. Now, that theorem holds if both of them are convergent series, they sum to a certain value. If you have a divergent series, this is a series that's going to go to infinity or negative infinity, if you multiply it by a non-zero value, it's still going to diverge. It's like taking infinity times 3. It's still infinity. If your first series converges, your second diverges, then if you add or subtract them, you're still going to diverge. However, there is an exception that happens sometimes, not an exception, but kind of a weird quirk. If both series diverge, occasionally, if you add them together, you can come up with a series that converges. Let me give you a for instance. If I were to take the series 1 over n, that diverges. Also, the series negative 1 over n, that also diverges. Okay, the first one goes to infinity, the second goes to negative infinity. But if I were to add these together, I would have 0. And if all of the terms are 0, it's a convergent series, it sums to 0. Okay, so you can have that special case. Then here I've got a couple extra notes. You can, if a series converges or diverges, you can add a finite number of terms to that series, and you're not going to alter whether it converges or diverges. Though if it's a convergent series, you will most likely change its sum. And the second one says, as long as we preserve the order of the terms, we can re-index a series without altering its convergence. So if you've got a series that initially starts at 0, you can change it so that it now starts at 1, for instance. We're going to end this section here by looking at 3 examples. We have 3 series here, and we're going to determine whether they converge or diverge. The first one is the series from n equals 1 to infinity of 2 over 10 to the nth power. And this is actually a geometric series. I could rewrite this as the sum from n equals 1 to infinity of 2/10 times 1/10 to the n minus 1 power. So I just have a geometric series where my a value is 2/10, the r value is 1/10. And a geometric series will always converge if that r value, or rather the absolute value of the r value, is less than 1. So this is going to converge. The sum here, we can find that. So let me write that it converges. Oops. The sum is 2/10, the a value, over 1 minus the r value, which is 1/10. So we have 2/10 over 9/10. So the sum would just be 2/9. Now the second one. We have the sum of from n equals 0 to infinity of n factorial over 1,000 to the nth power. Now I'm going to use the nth term test here. This one is going to diverge. Factorials grow faster than exponents. So that's just something that you can keep in mind. Factorials grow faster than exponents. So if I look at the nth term, so I'm not looking at the nth partial sum, just the nth term, and I look as n goes to infinity, so of n factorial over 1,000 to the nth power, again, because factorials grow faster than exponents, this is going to be have a limit of infinity. So by the nth term test, we can say that the series diverges. Now, this last one, we're looking at the series from n is 1 to infinity of the natural logarithm of n over n plus 1. In this case, I'm going to rewrite it a little bit. It's going to make finding my partial sum a little easier. I can rewrite this as the natural log of n minus the natural log of n plus 1. And that's going to help me when I find my nth partial sum. So for my nth partial sum, so I'm going to start from n is 1 and go up to n equals n. So we have the natural log of 1 minus the natural log of 2 plus, then now my n value is 2, the natural log of 2 minus the natural log of 3. Then moving on, the natural log of 3 minus the natural log of 4. And hopefully you're starting to see what's happening here. And we'll just continue this down to the natural log of n minus the natural log of n plus 1. So just like an example I did earlier, here we've got these two terms are going to cancel out. So the negative natural log of 2 and the positive natural log of 2. Negative natural log of 3, the positive natural log of 3. And those are going to cancel out all the way down. So what we're left with is just the natural log of 1 minus the natural log of n plus 1. The natural log of 1 is 0. So really, my partial sum is just negative natural log of n plus 1. If I look at the limit of this as n goes to infinity, as n goes to infinity, if I take the natural log of infinity, I'm still going to get infinity, but there's a negative in front, so my limit's actually going to be negative infinity, and this tells me that the series diverges. It's not going to go to a limit.